Hi everyone, today I'm going to show you how we can use the raytracer POV-Ray in order to simulate differential equations. The example that I'm going to use here is the one where we have an oscillator, a mass that can slide on a table and which is attached to a spring, and it oscillates, and I want the oscillation to look realistic, so I want it to satisfy the equations of motion. So here I'm going to simulate the motion by using the POV-Ray tracer. So if you look in the description of this video, you will find an archive that contains those 3 files so that you can see by yourself. So here, well, we have the description of the scene. You can go through it, but what is important for us is the equation of motion. So this variable here, x, will represent the position of the mass of the oscillator, and v will represent the velocity. M is the mass, which I arbitrarily choose to be 1 kilogram. K is the spring constant, and C the coefficient of friction of the mass on the table. So the force of friction will be proportional to the velocity. The force of friction is equal to C times V. dt will be our integration time step. So the smaller you make it, the more accurate the solution to the differential equation is. And t represents the current time. So in my simulation, I want to simulate the motion of the oscillator from time 0 to time 10. And this is specified in the config ini file. So I want 30 pictures per second. So I have here 300 pictures from 0 to 299, and my clock will run from 0 to 10. Okay. So well, as you know, the equation of motion of an oscillator is a second order differential equation. Well, here for simplicity, I'm considering a harmonic oscillator, but it works exactly the same if you add some nonlinear terms. Okay, so you can easily include nonlinear forces. There is no problem with this, but here for simplicity, I just consider the standard harmonic damped oscillator. So the equation is that the second derivative of the position plus this coefficient c over m times the first derivative plus k over m times the position, this is equal to 0. So once again, that's a second order differential equation, but a cool thing is that it can easily be replaced by a system of two coupled first order differential equation. And the advantage of this is that first order differential equations, they are very easy to solve numerically. So in order to do this transformation, all we have to do is to say, okay, let me take here the first derivative of the position, and I say, okay, I introduce a new variable, which is the velocity. Okay, you know, the velocity is the first derivative of the position. And now if I substitute in the original differential equation, if I substitute for x prime the velocity, then x second, that becomes the first derivative of the position. So we end up with this differential equation. Okay, so This differential equation, which is highlighted, has two unknowns, the position x and the velocity, but we have a second equation here, the fact that the velocity is the first derivative of the position. And now, in order to solve this numerically, it's very easy. All we have to do is to use the definition of the derivative. So for the position, the definition of the derivative is that we take the position at a time step later, an infinitesimal time step later than the current time. We subtract the position at the current time and we divide by the infinitesimal time step. Okay, so now if we take this definition of the position of the first derivative of x and we substitute in this first differential equation, we can solve for the position at time t plus dt, and we end up with this equation. Now we can use a similar definition for the first derivative of the velocity, so replace x by v, and we can substitute in this second equation, and we end up with this equation. Okay, so these are the two equations that we can simulate with POV-Ray, and the way of doing this is very easy. So what we do is that we are going to perform a loop over time. So as long as the time is smaller than the clock time that corresponds to the image that we are generating, we are going to loop. And we say that the new position is given by what? Well, that's what this equation here is telling us. The new position at time t plus dt is equal to the previous one, x at time t, plus the velocity times dt. So this is precisely what this equation is saying here. Okay, we do a similar thing for the velocity. Okay, and once we have this new position and the new velocity, we can update the current position here and the current velocity here with the new value. And that's it. We increment here our time step and we loop until the time of the simulation reaches the current value of the clock. And that's it. And then when we plot when we render the picture, we use this value of x for the position of the mass. Well, this is just a standard description of a scene. You can read this in more details if you want. Here, that's the position of the spring, and the position of the mass here. If I look at the object mass, you see that it depends on x. Okay, so each picture will be generated by taking into account the value of x, the value of the position of the mass. Okay, so now let us actually generate the pictures. So POV-Ray, config, oscillator, and here I'm generating the pictures. This will take a while because there are 300 pictures and I'm using a high resolution. Okay, so it will take about 20 minutes to generate all the pictures. So I'm gonna stop the video here and then I will resume when it will be over, when we will have the 300 pictures. And then I will put them together and we will see the video that we obtain. Alright, so all the pictures have been generated, and in order to put them all together into a video, I'm going to use Ffmpeg, So here is a command line. I have 30 pictures per second, and I'm going to compile all pictures that are named Oscillator with a 3-digit number into a single video, oscillator.mp4. So let's go for it. And this will be relatively fast. Just a few more seconds. Done. And now let us see the results. So open files. Oops. POV-Ray. Oscillator. And my video is here. Let us see. Nice. So the differential equations have been simulated correctly. Let's watch this once again. And it looks pretty realistic. And once again, you can add some nonlinear terms if you want. There is absolutely no problem for simulating them. So, well, if you liked this video, please give it a like. And I would appreciate if you can share it onto your social network. It doesn't cost anything to you to do that. Please share it on Facebook, on Twitter, or whatever social network you are using. You may also want to register to my channel so that you will see the other tutorials that I'm making. And I thank you for watching.